Good afternoon, everyone. Good afternoon. My name is Ed Schlesinger. I'm the Benjamin T. Rome Dean of the Whiting School of Engineering, and it is truly my pleasure to welcome you to the 2024 Don P. Giddens Inaugural Professorial Lecture Series. It's my pleasure to be here today with you to honor Hedy Alavi, a teaching professor of environmental engineer in the Department of Environmental Health and Engineering, the Associate Dean for International Programs at the Whiting School, and the chair of the Engineering for Professionals Master's Degree Programs in Environmental Engineering and Science, and Environmental Planning and Management. An expert in hazardous and solid waste engineering and management, Hedy was previously the chief of the Design and Certification Division of the Solid Waste Program in the Waste Management Administration of the Maryland Department of the Environment. And he is currently the chief examiner and state representative for Maryland and DC for the American Academy of Environmental Engineers and Scientists. He is also the recipient of numerous awards for teaching and public service, including the 2007 JHU Alumni Association Excellence in Teaching Award for the Whiting School of Engineering, the 2005 Education and Public Service Award from the university's Council on Water Resources, the 1998 Excellence in Teaching Award for Johns Hopkins Engineering for Professionals in Whiting, and the 1992 Merit Award from the State of Maryland Department of the Environment. So as such, it should be no surprise that he's developed several graduate degree programs in the environmental field, and clearly he is an excellent teacher and mentor. This afternoon, we're going to hear about how landfilled waste is a big problem for local municipalities and really our country as a whole. And while we strive for zero waste solutions, we have a very long way to go, and Hedy will elucidate some of those hurdles for us. But there is hope, and Hedy will highlight some of our areas of success as well. I'd like to take a moment to recognize one of my predecessors, Don Giddens, for whom this inaugural professorial lecture series is named. Don Giddens was the 5th Dean of Engineering at Johns Hopkins and a professor of mechanical engineering. I want to offer my congratulations to Hedy. I know that a number of people will be offering their congratulations, but I want to do that first, and also to say how valued a member of our deanery he is and how many good things he has brought to the Whiting School of Engineering. And now it's my pleasure to introduce Marcia Wills-Karp, the Anna M. Bacher Professor of Environmental Health and Engineering and the Chair of the Department of Environmental Health and Engineering at both the Whiting School and the Bloomberg School of Public Health. Marcia.
A little bit shorter than Ed. I was given the pleasure, the honor to introduce our speaker today, who will introduce Hedy. But since I have the mic, I'm going to take the prerogative of saying a few words about Hedy. Oh, somewhere I lost my glasses. Hold on. So I too want to add my heartfelt congratulations to Dr. Hedy Alavi on his promotion to teaching professor, but also in being honored by this inaugural professorship. So congratulations, Hedy, and I think we should give him a round of applause. So Hedy is an outstanding educator, professional engineer, and colleague. His passion for teaching is exemplary, and his quest for academic excellence, rigor, and fairness are hallmarks of his distinguished teaching career. In the words of one of his students, your passion for teaching is infectious, and your creativity brings learning to life. Very true. Hedy brings a unique perspective to his teaching in the department as he draws upon, as Ed mentioned, his extensive professional and industrial experience. He taps into the professional network to bring in real-world projects to our senior design course. His stature in the field and his connections with environmental engineers has enabled us to partner with professionals in the field, and some of them are here today, to provide an outstanding undergraduate design experience for our students. Moreover, through his professional, he's also brought in guest lectures, and they cover a range of topics from current industrial practices to environmental and professional ethics, which is very critical in this field and many others. He's an exceptional colleague, and he brings kindness and compassion to all of his interactions with students, faculty, and staff. He gives 200% in all he does. On a personal note, I've had the privilege of working with Hedy since the inception of our new department, and I value his counsel, his support, and friendship. So I will turn to my real job up here to introduce our distinguished guest. It's my privilege to introduce Dr. Alavi's mentor, Professor Emeritus Keith Bedford, who will introduce Hedy in his lecture. So Professor Emeritus Bedford was a faculty member at The Ohio State University for 33 years. As chair of the Department of Civil, Environmental, and Geodetic, is that correct? Okay, engineering. He brought his integrative skills to restoring the research vitality of that department. And it sounds like he brought a lot of innovation to the department. Yeah. And he received his PhD from Cornell University, has over 200 publications and an outstanding national and international reputation in coastal and environmental engineering. He's specifically known for his research in environmental fluid mechanics and transfer phenomena. He performed award-winning research in the areas of turbulence, model, structure, and formulation, created a new acoustic instrumentation necessary to measure, for the first time, sediment entrainment and resuspension remotely and directly in coastal and estuarine water bodies. He created the first coastal forecast system to make operational regular predictions of currents, temperatures, trace constituents in coastal water bodies. This is critical for the current time that we're in with climate change and other challenges to our waterways. So we thank you for that innovation. He's received numerous awards. He received the Carl Emil Hilgard Prize, the Huber Prize, State of the Art Civil Engineering Award, the American Meteorological Society Special Award, and the another honor that was bestowed on Professor Bedford was that he was elected as a fellow of the ASCE. The Board of Trustees recognized his contributions to the Ohio State University by establishing an endowed scholarship fund in his honor. So congratulations on this achievement. And as Hedy's longtime mentor and friend, we are honored to have Professor Bedford here with us today to introduce Hedy's presentation. So please join me.
These should pass.
They're not mine.
Okay. Let's see. Here we go. Thank you. This person you were describing is that the person that really happened, Marilyn? In any event, thank you very much for having me here to do this introduction. Hedy Alavi was a special and a very intelligent person. And it's a great honor to be here to acknowledge that. I would like to say that with all this stuff about turbulence and everything, that I had a lot to do with many of the things that, as you heard, he undertook. My only ability to mentor him in the area of landfill technology was in my role advising his dissertation. And his dissertation had to do with creating a technique for analyzing what at the time was an instrument that would develop enormous quantities of data about the spatial and temporal structure of sediment floating around at the bottom of water columns. Now, I'm going to define the word enormous in a couple of minutes, but so Hedy teamed with a very interesting person in chemical engineering and constructed with this technique. Between the three of us, we constructed this wonderful technique, but it required many trips to the computer center. And we didn't have, computers sitting on your desk back in those days where you could just sit there and go, send it off and stuff would come back on the screen and you could just either print it out if you wanted to or store it someplace else. We didn't have any of that stuff, okay? You went to the computer room and you picked up your output. And there are many old people like me who are nodding, yes, I remember those days. And the output, from Hedy's calculations were very large and very thick. And he would go over there and pick these things up and he'd come back to his desk and he'd sit down with the calculators, right? And type things up and tap and figure things out and do all this other stuff, make changes, go back and start the whole process all over again. Slowly but surely over the year of his dissertation, building up piles and piles and piles of paper, that he stored in a variety of different places. And one talks about solid waste. I couldn't think of an easier place to start than that. And I swear that that's the first time he got a touch of the, what do I do with all this stuff, that kind of drove a bunch of the stuff that he now works with. Other people have ably defined, and applauded him for the things that he has done. I would like to take the last little minute or two here to point out that Hedy came to us during the late 60s and, late 70s, early 80s. This was a very, very bad time in his home country of Iran. And we had a student who was beset upon by a country being torn apart, between dictators being deposed and religious people going berserk, doing this, that, or the other thing, including kidnapping hostages. These activities extended somewhat to campus. And here is Hedy stuck in the middle of this. And it wore on him. This was a difficult time for him. And in my mind, and I hope he doesn't mind my being so personal about this, but in my mind, this was an enormous thing to overcome and satisfactorily complete his dissertation. And he mentioned when he and Manu were leaving that he probably wouldn't hear. We probably wouldn't hear from him for a little while, and it was more than a little while. And then all of a sudden, he showed up about 20 years later, and he was as happy as we had ever seen him. And he just was bubbly in his descriptions of the things that you had heard, that he was involved with and how happy he was integrating people, creating new programs, solving problems that were of importance, none of which had anything to do with what I taught him, but nevertheless, and it was so nice to see him so pleased and so happy, and his accomplishments are a reflection of his ease in the system that he's now in. So I'm gone over my time. I introduced you Hedy Alavi, and he will speak to us about highly engineered containment systems, not just dumps. Okay.
Good afternoon. Well, I guess the only word that it came to my mind is I'm truly humbled. Thank you so much. I really appreciate it. With that, Keith, Professor Bedford, thank you so much for your kind and inspiring remarks, and most importantly, for the valuable mentorship that you provided me. During my time as a graduate student at Ohio State University. Yes, the time was tough. However, your academic contributions have made a lifelong impression on my mind, and your caring personality has had a lasting impact on my heart. And yes, I'm happy to inform you that my interest in human rights has remained strong. Also, I thank your wonderful wife, Marilyn, for accompanying you on your long trip from Maine to join us for this occasion. Thank you, Marilyn. Dean Schlesinger and Department Chair and Professor Wilskarp, thank you for your outstanding and visionary leadership and unwavering support for many years and in many ways. Thank you. I am delighted to be a part of the Dean's Office, the Department of Environmental Health and Engineering, as well as Engineering for Professionals, especially during this exciting and flourishing time that Johns Hopkins, in particular the Whiting School of Engineering, is experiencing. I have been honored to be a member of this prestigious institution for the best 30 years of my life. My office is located not far from the campus bell tower, and its chimes always remind me how fortunate I am to be an educator on this beautiful campus with its talented students. I would like to express my sincere appreciation to every one of you for taking time and being here, present here during in this beautiful March day. My special thanks go to renowned faculty, my distinguished colleagues in the Dean's Office, my professional associates, my dear friends, and my amazing students. I am grateful to the members of my family, most of whom are here today on second row, perhaps some in the back. My special thanks to my artistic wife, Fariba, and my children, Sharon, Charlie, Ryan, Ida, and their spouses, Josh, Amin, and Spencer. Also, my cousin Benaz and my extended family in Houston, Texas. Also, I had a surprise here today. And that was my grandson, Colin, my handsome grandson. And I think he's happy to miss school to join us. By the way, I also mentioned the chimes also, they occasionally remind me that I'm running late for meetings, and and classes. And perhaps that's was almost happening today. Hopkins really holds a special place in our heart. It played a significant role in my children's teenage years. They were here around the campus visiting my office. Lastly, I would like to cherish the memory and perhaps more importantly, the legacy of my colleagues in the department who passed away during recent years, including Professor Ed Bauer, Professor Charlie O'Melia, and Professor Rez Woolman. Getting to my lecture topic is landfills, highly engineered containment systems, not just dumps. I will discuss design, construction, and management of solid waste landfills. The presentation is brief, and I would like to emphasize that the target audience for this presentation is broad. So if you do not see differential equations for contaminant transport, don't get disappointed. So with that, these are the outline, the topics that I will be covering very briefly: municipal solid waste generation and hierarchy in the US, role of landfills in MSW management, environmental risks posed by landfills, location restrictions for landfills, landfill operation, major design components and construction, environmental monitoring systems, modern-day landfills, issues and instrumentations, and opportunities for post-closure development. I would like to establish the significant role that landfills play in waste management in the US. Starting with waste generation, this graph obtained from EPA's latest report shows the trend in solid waste generation in the US from 1960 to 2018. As you can see, there has been a continuous increase in waste generation due to population growth. I estimate that at present, there are more than 300 million tons of solid waste generated in the US. This slide shows the hierarchy of solid waste management in the US. EPA considers landfilling as the least preferred or least desired method of solid waste management compared to other available options such as source reduction, recycling, and waste to energy. That I totally agree. However, please look at this slide, the graphs. This chart shows how solid waste is managed by different methods over time in the US. Despite waste reductions by regulators, by private entities, by public entities, still 50% of the waste is being deposited in landfills. So the zero waste notion will remain a challenging and ambitious goal. And this is the highlight: the landfills will continue to play a significant role in solid waste management for the foreseeable future. Also, it is notable that the number of landfills across the US has declined continuously. If you remember, the base generation has gone up. And the main reason is these landfills are turned into private, regional, and mega landfills. This is to take advantage of economies of scale and cost reduction. So with that, I guess I missed one. Sorry. Yes. So what are environmental risks posed by landfills? There are many. Okay. The most important one is really migration of leachate to groundwater and contaminating the groundwater and surface water. What is leachate? Any rain that comes in contact with waste or any water that has been generated from the decomposition of the waste and percolates through the waste and gets to the bottom of the landfill, collects at the bottom of the landfill, is called leachate. It has a lot of harmful chemicals, such as toxic heavy metals, dissolved organic, ammonia, and many more. Other risks include greenhouse gas emissions, methane and carbon dioxide, aviation bird hazard, and altering bird migrations. This is an interesting topic because birds during the winter time, the landfill is warm, there is food, there is water management systems there. So why do they fly? So what are municipal solid waste landfills? As it was in the title, these are highly engineered containment systems for disposal of MSW. They are designed, constructed, and operated to minimize adverse impacts on human health and environment. The rest is perhaps not as important. Landfills cannot be located near or in environmentally sensitive areas. These include airports because of the bird hazards, wetlands, 100-year floodplain, faults, seismic impact zones, and unstable areas. Just to get you acquainted with landfill operations, these are some general terminologies that are being used. Working phase is the place that solid waste is being deposited and compacted. Cell is the volume of waste and daily cover placed during one operating day. If they work during the night, that's one operating period. Lift is a completed layer of series of adjoining cells. For example, in this case, we have several cells and 1.5 lift. And daily cover at the end of each each day, we cover the waste with 6 to 12 inches of soil or alternative materials, could be foam products or geosynthetic. What are the purpose of daily cover? There are many, but some of them are odor, preventing odor. And perhaps one of the most important one would be fire, preventing fire, and disease vectors, bird attractions, and so forth and so on. That landfill major design components include a base liner with leachate collection and removal systems, gas collection, recovery, and utilization, closure cap, surface water and drainage control systems, environmental monitoring systems, and post-closure development. So this depicts a general schematic of the vertical cross-section of a landfill. I will provide you with more details in my presentation. The blue zone depicts the groundwater. The brown zone implies the buffer zone from the bottom of the landfill to the groundwater. Then we have a compacted clay liner with a synthetic liner on top of it. The purpose of this liner is to prevent leachate migration to groundwater. Further up, we have drainage layer to convey leachate. There are also sumps for leachate collections and pumps to remove them. And also, as you see, there are monitoring systems such as groundwater and groundwater monitoring and gas monitoring systems. And then, as I said, when we get to the top of the landfill, we cap it, that I describe it momentarily. So let's get to the interesting part. I will present several natural and geosynthetic material used in landfill construction, starting with clay liner. The purpose of the clay liner is to prevent leachate migration to groundwater. It is compacted. The thickness is 2 feet. It is constructed in series of compacted 6 inches thick lifts, and you must bind them together properly. A key parameter is the hydraulic conductivity, or the coefficient or permeability that governs the flow of liquids in porous media. In this case, please look, it is really, really minimal. This means 1/10 million centimeter per second. Then we have, and instead of this, we have that actually could replace this. We have something called geosynthetic clay liner that could substitute the actual clay liner. It is a layer. I brought some samples for you. There is a layer of pure bentonite backed by geotextiles. It requires less space. Please pay attention to this. And it's about 2 feet, you have this. And it saves landfill's capacity. It's interesting, when it encounters any water or leachate, it swallows, expands, loosens up, expands, and basically patches the hole from the bottom. That's the purpose of this product. It's called GCL. Remember that, please, because we are going to build a landfill quickly. And on top of the 2 feet of clay or GCL. In order to add protection, we add something called FML or flexible membrane liner. And this is the way they are seamed together. And I apologize, I am behind. Okay, this is geosynthetic clay liner, I apologize. And this is the geomembrane. This is this one. And this is the way it is anchored to prevent a slippage. All right, so the combination of this and the GCL or the clay liner, it is called a composite liner. Then we have this up here. This is called a geopath. It has a lot of applications. One is we put it over FML, the plastic, to prevent it from puncturing. The other one is a wonderful filter, and that protects basically fine materials to clog drains. So this is a geopath right up there. Then we have granular drainage layer. The purpose is to collect and convey leachate. Thickness is 12 inches. And we need series of drains and pipes to collect leachate. One design parameter is the maximum leachate height above the liner should not exceed 12 inches. And this is one technology used. It is called sloped terraces. These are items the materials that could be used in a drainage layer. Please note, we could also use shredded tire as a way of recycling used tire. Okay, this is interesting. Another construction material is called GeoNet. This is a 3-dimensional, highly transmissive for conveying leachate. So keep in mind, instead of 12 inches of sand or gravel, you could just use this one. So it saves a lot of landfill space. However, keep in mind this clogs. So in order to prevent it from clogging, if you remember, we use a geopath to cover it. Okay. Now we have to remove leachate. There are gravity flow where the land slope allows. In this case, we don't need pumps. We save some cost of pumping. However, it needs to penetrate through the liner and might create some issues in the future, some leakage. Otherwise, we use sumps. We install sumps to collect leachate and pumps to remove them. Also, we need risers and manholes to access and clean up. Leachate management facilities include line leachate pond, leachate holding tanks, and discharge to wastewater treatment. Please note that in this case, we might need pre-treatment. Leachate treatment methods include biological methods and chemical and physical, and there are many subcategories of this. Another way to manage the leachate and is to recycle the leachate through a specially designed landfill, through the waste, and recycle it. There are several advantages. First, it enhances biological degradation of organic waste by adding moisture and nutrients. It maximizes landfill gas generation for energy recovery. It reduces leachate treatment and disposal costs. It also causes rapid settlements, volume reduction, and stabilization. Now let's switch to gas. Landfill gas constituents include principal gases, mainly methane and carbon dioxide, almost 50% each, depending on the life of the landfill, and trace gas compounds that they are being generated at very low concentrations. And please note that methane and carbon dioxide are both potent greenhouse gases. Landfill control gas, there are two methods. One is passive method. In this case, the driving force is the gas piled up and pressure inside the landfill in itself. The gas production is limited. Examples include pressure relief and interceptor trenches shown here. Another method is active method. Energy is in the form of an induced vacuum, and the generated gas is utilized for energy recovery. Vertical and horizontal gas extraction wells shown here are examples. In order to use landfill gas, we need to basically clean it up or purify it. Carbon dioxide and methane are separated using some different technologies. Hydrogen sulfide and moisture are removed. And the conversion technologies include internal combustion engines. This is for projects with up to 3 megawatts of production, and gas turbine for projects with more than 3 megawatts of production. Okay, now that we have learned some stuff about the landfills and have gotten acquainted with different landfills components, let's build a landfill from the bottom liner and leachate collection system to the top closure cap, perhaps in 2 minutes. I am sure, the reason I put it here, I am sure that you appreciate how many layers with detailed standards and specifications are required. No worries. I will cover the colorful layers only, and the students must learn the details provided in the right-hand column. So let's start with the blue region at the very bottom. that depicts the groundwater. Then we have the buffer zone. We cannot dig into groundwater to build landfills. Then we have 2 feet of compacted clay with low permeability. Please remember, instead of this, we could use GCL. I can't find it. You could use this guy, GCL. In order to add protection, we have FML on top of it. In order to protect FML, we put a GCL over it. Oh, I apologize. A pad over it, GO pad over it. Okay. And then we put the drainage layer over it. Okay. In order to protect this, we have another layer of GO pad over it. Okay. So it's not sometimes they come like this, and manufacturers have made the life easy for us. And then, so that is for drainage layer. We could use granular or that geonet. Then we have a protected layer, and then we can start putting waste. Please note that the first four feet, they should be, we call it soft trash, because you do not want to damage the liner. Then after it gets to the final elevation, which is designated in the permit or by design, we cap the landfill. Again, this is the last top MSW lift. We have a foundation. Then we have a gas vent. We have 18 inches of low permeability compacted clay. Please note that the specifications for this compacted clay is less stringent than that in the bottom liner, because on the top, you are preventing rain to become leachate. In the bottom, we are preventing leachate to migrate into groundwater. So in this case, then we have an FML for added protection, drainage layer to convey rainwater, 12 inches, and instead of that, we could use GeoNet. Then we install geotextile to protect the drainage layer. And finally, there is 2 feet layer of soil with the 6 top inches being topsoil that is suitable for vegetation growth. Now that we have built a landfill that's protected, we need to have surface water and drainage control systems. It collects and diverts surface water off the landfill surface. These include benches and downshoots, infiltration basins, and so forth and so on. And a couple of examples are shown here. This is a downshoot, and this is a bench designed. Then we have to monitor landfills. There are 2 major systems. There are many, but 2 major systems. One of them is groundwater monitoring and response program, include detection monitoring, assessment monitoring, and corrective action monitoring. These are basically successive levels. Then we need groundwater monitoring system, minimum of 4 monitoring wells, 1 up gradient, 3 down gradients, sample frequency semi-annually or quarterly, and we need 4 independent samples. And students really know a lot of hydrogeology to be able to take independent samples. The next item is gas monitoring. There are gas probes that they are installed outside the waste pile, And air monitoring, please note, this is not a gas extraction well. This is just a gas probe for monitoring. Air monitoring, we need to look for explosive gases and hydrogen sulfide and monitor those. Soil is monitored for differential settlement, slippage, and surface erosion. Then with regard to modern day landfills issues that we are encountering, one of them is really the climate change that increases flooding and erosion on landfill sites, especially on locations close to coastal zones. Emerging contaminants in landfill leachate pose major challenges for water treatment facilities. These include micro and nanoplastics and PFAS. High-tech instruments such as drone and GPS increase the operational efficiency, safety, and monitoring performance of landfills. For example, they detect excavations that pose danger, reduce operational failures, and determine landfill volume remained. And high-tech in-situ sensors, they provide valuable real-time feedback and accurate cost-efficient information. For example, sensors detect subsurface fire that damage liner. They measure the height of leachate over the liner, and they also detect combustible and toxic gas, and also in-situ video cameras that monitor leachate collection systems. Post-closure requirements, they include routine inspection and maintenance of infrastructures, repair of differential settlements. This is due to different decomposition rate. And you need to basically continue this for at least 30 years. Lastly, these are some sustainable and innovative approaches for the end use of landfills listed here. I need to point out that any use of the landfill at the end, any end use, any project, they must not interfere with the function of the following: CAP, gas extraction and control, runoff control, and environmental monitoring systems. Examples include golf courses, ski slopes, wildlife habitats, solar and wind energy. And this image on the right-hand side is an example of a landfill solar project in Annapolis, Maryland. Also, landfills could be used as a training site. And these are a student on a field trip to a landfill in Baltimore. And I would like to thank you with leaving you with this, I would say, harsh transition from engineering to art. And the artist behind this painting is my wife, Fariba. I know that much for the painting. Thank you so much. I really appreciate it.
Hi, I'm Ed Scheinman, Vice Dean for Faculty. Hedy, thank you for a very informative and important presentation, and my heartfelt congratulations on your promotion to the rank of professor. We have a little memento for you for this occasion. Congratulations. One more for Hedy. And you can mob him at the refreshments. I'm sure he would love your greetings. Good evening, everyone.
Thank you.